Hi, in this video, we'll be going to discuss the notion that we've built upon about limits to discuss properties about functions. So let's begin with the idea that you have a function and you draw its graph. Imagine you draw the graph and you can draw it in one motion without lifting your pen. That means there is no breaks in the graph, and so we say that this type of graphs, this type of functions are continuous. So what does it mean to be continuous and having no break in graph? Well, let's say you have a point on the graph at a, x equals to a. If the function was defined over here, where x does not equal to a at this point but over here, such as what we have learned about continuous extensions of graphs, but this is like discontinuous. If we were to draw to this point, we need to lift our pen, put a dot here, and continue drawing. And so this is what it means to have a break in a graph. And so, to be continuous, it just means that the limit of the function as x approaches a will equals to what the value is of the function is at a. And so it's captured by this equation. And so, things to note for this function to be continuous, firstly, is that fa must be defined, the limit exists, and equals to fa. And so, we take the example y equals to x plus 1. We see that the limit as x approaches 2 of fx equals to 3. And this is equals to f2. And so, f is continuous at 2. And then if you can show that for all x, f is continuous in its domain, then we say f is continuous on its domain. And so really the notion of continuity is to ensure that there is no breaks in the graph. We'll see how we use this continuity to help prove certain theorems at the last part of this video. But first, let's talk more about continuous functions. Some non-example is the function where its f equals to x plus 1 at all points outside 2 and 0 when x equals to 2. We have already seen that if x equals to 2, if it's continuous, it should be 3. But now we redefine it to be 0. And so when we take the limit, it will still be 3. But now f2 is 0, and so we say it's not continuous. And this form of discontinuity is called removable discontinuity, where fa is defined but not equals to its limit as x approaches a. But we can redefine a new function to let it equal to the limit, and this will just be called the continuous extension of f at a. Another form of discontinuity is when the graph approaches infinity at a point. The vertical line will then be called an asymptote, and f will have said to have an infinite discontinuity. For example, y equals to fx, which equals to 1 over x squared. As x approaches 0, from the left or the right, fy approaches infinity. And so we say that 1 over x squared has an infinite discontinuity at x equals to 0. Now, another form of discontinuity is the jump discontinuity. And that can be seen when the left hand side and the right hand side limit do not agree with each other. Remember from the previous video, we have already said if the limit exists, then the left hand side and the right hand side must equal to each other, and vice versa. And so, if the left hand side and the right hand side do not equal to each other, or the limit does not exist on either side, then f cannot be continuous at that point as well. And we call this a jump discontinuity. With the idea of that, let's talk about certain properties of continuous functions, which you can easily prove by yourself, and it's in the textbook by Stewart Calculus or Thomas Calculus. So I'll leave it to you to read that on your own. But you can easily show that if you multiply a scalar to the function, it is still continuous. Adding two continuous functions makes it continuous. The product or quotient of two continuous functions is also continuous. And this allows you to prove that polynomial and rational functions are continuous. You can now see how important continuous function is and how useful it is when you want to play with it, because you can just add two continuous functions and it remains continuous, and we can just say like that means they are closed under addition. Another property that is very useful for continuous function is the substitution property. For example, you have the limit of x approaching a. We can replace x with a plus h. So it means that x is over here, which equals to a. Now, you're taking the point a and then you're reducing the error term of h. And we can actually say that the limit will now be equal. And the proof follows because you want to just prove that this limit as h approaches 0 of f a plus h equals to L, which equals to the limit as x approaches a of fx. So let h equals to x minus a or x equals to h plus a, either is fine. Now given an epsilon, we want to find a delta such that the following occurs. Since we already know this limit exists, we can find a epsilon and a delta. We can take any epsilon and find a delta such that x minus a is less than delta. Imply this, and if we just sub in x here, this delta 1 will work, and so we achieve to prove that the limit equals to L. And we can actually reverse the order to prove that if this is equals to L, this will has to be equals to L as well. And so we can actually do a substitution of limits. And so with that, if we already know that the function g is continuous, the composite function will just equals to gb. The proof follows the same idea, as all we need to do is combine the relations. Since we know g is continuous, we can find a delta such that when y is in the interval, gy minus gb is less than epsilon. And we know that this limit exists. So there is another delta such that x minus a less than delta implies that fx minus b is less than delta over 2. This delta over 2 corresponds to over here. And now when we combine the relations, we take this delta, fx minus b is less than delta over 2. We replace the y here by fx, and we get g of fx minus gb is less than epsilon. And so this, we found an appropriate delta, which allows us to say that the limit as x approaches a of g fx equals to gb. And because b is this, we can actually write this as like that. And so we can push the limit operator into the composition, and we just say that the limit operator commutes with continuous functions. And if even better, if f is continuous, then b is f of a, which means this will be g of f of a, which equals to g circle f of a, which means that if f and g are continuous, f circle g is continuous, or g circle f is also continuous. And this is very useful as it allows us to create more and more continuous functions from O1s by doing the composition. Lastly, an application of this continuous function is proving the existence of roots through the intermediate value theorem. The proof of the intermediate value theorem is omitted for this basic course, but you can feel free to read it up on your own to have a better understanding. But I'll give you an intuitive explanation about it. Suppose that f is a continuous function on a closed interval a to b. Then a and b do not equal to each other. So that means you can draw a graph as the following, or it goes down depending. For any points from a to b, such as n over here, we know there is no break in the graph, and so this line must intersect with this graph at a certain point. And so there exists a point within the interval such that fc equals to n. And we can use this to show the existence of roots, such as the following. For example, we get the following function here. And let's say we do not know how to find roots. Then, we just need to find 2 points such that they are different in sign. For example, f minus evaluated at -1 is -6, and f evaluated at 3 is 6. And so, we know it transverse from -6 to 6 in some fashion. And so it must cut the x-axis at a certain point. And so we can say there exists a root such that fc equals to 0. But what I would like to take note is while this intermediate value shows the existence of root, it does not help us find the root or tell us how many roots there are. But at least we know there is an existence. We can apply other forms of methods to find it, which we can learn in numerical analysis in other courses. And so now you can see the property of continuous function is to capture the idea that there's no breaks in the graph, which allows us to use this intermediate value theorem, and it also is closed under addition and composition of functions, which allows us to create more functions, and hence you can now visualize the utility of having continuous functions. Thank you for listening, and I've come to the end of this video. Catch you in the next one.